All right, one thing before we get to the second FRQ, I realized I did part B the long way. Again, the really long way is to use the formula for do IDX. The second longest way is to come up with your equations for X and Y and do derivatives of those equations at this 2.466 number. I forgot when I recorded the video, but we did this in class. You can switch to polar mode on your calculator. And if I want to find dy dx at a certain point and I'm given a polar equation, I can just type this equation into the r equals. So here's the polar equation. We want to find, I did still need to find where that point was x equals -2. Like I still needed to find that theta in function mode. But now I can go to second trace and have it find dy dx for me at 2.466. I'm just typing this whole thing in. So that did give me the same slope that I got before. So now I did still, to get the theta that I needed, I did still need to know that r times cosine theta is the equation for x. So r times cosine theta. I did need to set that equal to -2. And the only way you can solve that is in your function mode. So you've got to be in function mode to find the intersection of two graphs. All right. On to the second problem. We're still calculator allowed here. So this says the graphs of the polar curves r equals 2, which is the circle centered at 0, and r equals 3 plus 2 cosine theta are shown in the figure above. The curves intersect. Oh, they've done this for us. They intersect at 2 pi over 3 and 4 pi over 3. So for sure that's 2 pi over 3, quadrant 2, and this one is 4 pi over 3. Let R be the region that is inside the graph of r equals 2 and also inside this 3 plus 2 cosine x. Find the area. So we have this symmetric area right here. So if I could find this area, I'd be in pretty good shape. And I think what I need to do is figure out, let's see, starting on this, start at the center. We're definitely on the circle first, right? We're on the circle, The only time we skip back over to the 3 plus 2 cosine x equation is after this point of intersection, and then it switches to this. And so if I double that area, I should be good. I just want to confirm that this is theta equals 0, and I want to confirm that this is theta equals pi. So how do I confirm that? Well, I just sort of double check that, like, yeah, if I'm on the r equals 2 equation and I plug in 0, the answer is just 2. So face 0, go out 2. So yes, this is where the circle starts. And then for the, I always forget, is it cardioid or cardoid? I don't know. Anyway, for this equation, I want to plug pi in, and that would come out 3 plus 2 times -1. So 3 minus 2 is 1. So yeah, we would face pi and go forward 1. So yes, this point on the 3 plus 2 cosine theta curve is sitting at pi. All right, so for part A, you don't have to do this. I just like the visual. I like to remind myself to do this. I'm going to double the area of the red circle first, so this section, and then I'm adding to that the little, I don't know why my pen's so spotty, the little section of the cardioid. There we go. So I'm adding that little piece of it. That's just my visual reminder. I just like doing that, so I keep everything in order. All right, and then the formula is, so that's 2 times, remember the formula in general for area is 1/2 integral from a to b of r squared d theta. So let me try to get my pen back in writing order here. Okay, so 1/2 the integral. So the red circle portion goes from 0 to 2 pi over 3. So from 0 to 2 pi over 3. And r squared, 2 squared would just be 4. I'll just write 2 squared just so you can see the formula. And then we're adding to that the area, so 1/2 integral from 2 pi over 3 to pi of the other r squared, now that we're on that section. 3 plus 2 cosine theta, that gets squared d theta. All right. I keep bothering to write out the 2's, even though I know every time the 2's and the 1/2's cancel. Sometimes we're just finding an area and we're not doubling anything. We're finding the whole area. So I don't want to forget to put the 1/2 in. So that's why I always set this up, even though it usually cancels out, because we're often doing these symmetric areas. But sometimes they give us something that, you're not using symmetry. You're going all the way from like 0 to pi or finding the whole shape. Anyway, the rest of this goes into my calculator. It doesn't matter what mode you're in for this, so you can be in function mode. Really the only time I would switch to polar mode is to find a dy dx, just because that's a lot easier. So this is 4 d theta. And remember, you can't combine these because their integrand, or the integral bounds are different. So plus math 9. You do want to make sure that you're typing things in correctly. The number of times that a student has something written out correctly, but then has the wrong numerical answer is pretty often throughout the years. And I think that just comes down to not having practiced a lot, like saying, yeah, I know how to type that in. And it's easy to make a mistake because of all these parentheses. You can also put these two expressions into your y1 and just doing like y1 squared plus y2 squared, or whatever. All right, so I'm getting 10.370. So that's my final area for part A. For part B, a particle moving with non-zero velocity along the polar curve given by r equals 3 plus 2 cosine theta has this position, x of t, y of t, at time t with theta equals 0 and t equals 0. This particle moves along the curve so that dr dt equals dr d theta. Find the value of dr dt at theta equals pi over 3 and interpret your answer in terms of the motion of the particle. So remember, motion of the particle is when we're talking about dr dt and things. We did this in the last one. That's saying like, is the curve getting farther from the origin or closer to it, basically. You could also say something about it if r is increasing or decreasing, but it's mostly about how the curve is related to the origin. Okay, so for part B, what are we supposed to do with this? So we want something about dr dt. We have an equation for r in terms of theta. So because dr dt is equal to dr d theta, and we're not given any number for like dr d theta equals 2 like we were in the last problem, I'm going to go ahead and find the derivative of r just with respect to theta. Just take this derivative. So that's 0, and then this becomes minus 2 sine theta. So this is dr d theta. And remember, dr d theta is equal to dr dt. So dr dt is also negative 2 sine theta. We're supposed to evaluate this at pi over 3. So yeah, dr dt at theta equals pi over 3. It's just equal to dr d theta at pi over 3. So negative 2 times the sine of pi over 3 is radical 3 over 2. So the answer is just negative radical 3. So that's the first part. Find dr dt at pi over 3. We did that. Interpret this answer. So dr dt is negative. That means that r is decreasing, right? But then when we're talking about motion of the particle, if you want to figure out if it's getting closer to the origin or farther from the origin, you need to look at whether r is positive or negative. So I can start by saying this. Sorry, two things. dr dt is less than 0, so r is decreasing. Let me start just by saying that. Like the length of the radius is decreasing. Or that could mean that a negative radius is getting longer, more negative. So that's the other part of it. So what is r of pi over 3? R of pi over 3 is equal to 3 plus 2 times 1/2 cosine of pi over 3. So 4. So r of pi over 3 is greater than 0. So we've got a positive radius, but the radius is decreasing. So that means that it's decreasing. So that means that if you've got something positive but r is decreasing, we're getting closer to the origin. Also, just estimate where pi over 3 is. As you continue this on, you are getting closer to the origin instead of farther from it. So the curve, motion of the particle. The particle is getting closer to the origin. All right, for part C, for the particle described in part B, so we're still on this cosine curve, 3 plus 2 cosine, dy dt is equal to dy d theta. Find the value of dy dt at pi over 3 and interpret your answer in terms of the motion of the particle. So we'll talk about the motion in a second. Let's do the same thing we did before. Now, I used the r equation and took the derivative with respect to theta. They're not giving me explicitly a y equation, but remember, every y coordinate is equal to the radius times the sine of theta. So y is equal to 3 plus 2 cosine theta times the sine of theta. And you can find the derivative of that. Now, we have a calculator and we're just evaluating. So I don't need to do product rule to find what y prime is. I can just say dy d theta evaluated at theta equals pi over 3 is approximately, I'm going to let the calculator do this. So math 8. It's not that we can't find the derivative, it just would take time. And time is often something that we don't have a lot of when we're taking these tests. So to 3 places, it's 1/2. I bet if we did this without a calculator, it would come out to exactly 1/2. So I'm still just going to show that I rounded it. And that is equal to, the question was not find dy d theta, it was find dy dt, but dy dt is equal to dy d theta. So that's also dy dt at theta equals pi over 3. I don't know if it matters, that I name it like that or not, but that's part of it. And then what about this motion? So when you're talking about dr dt, the motion is like, are you getting closer to the origin or not? Because a radius by definition is the distance to the origin, right? So that's why we're always talking about, are you getting closer to the origin or not? Y is the distance from the x-axis, right? If I say y is 10, you're 10 units above the x-axis. So this dy d theta is positive. So dy dt is greater than 0. And is y positive or negative? Let's see. Y of pi over 3. That's equal to, so let's see, 3 plus 2 times cosine of pi over 3 times radical 3 over 2. That's all positive, right? So, and y of pi over 3 is greater than 0. So you have a positive y value, and the y values are just going to increase after that point. So the particle is moving away from the x-axis. These interpretations are pretty involved. I wanted to make sure that we practiced this. You do have a little bit to interpret on your test, but you don't have all of these interpretations for the test. But it's good to look at because I've noticed these popping up in more of the recent AP free response questions. All right, I think we've got time for one more in this video as well. So this one is no calculator. So let's see how this goes. Your free response will be calculator on the test, but we do have multiple choice that are no calculator, so some of these skills might come in handy. Okay, the graph of the polar curve, this, from 0 to pi, is shown above. Let S be the shaded region in the third quadrant, bounded by the curve in the x-axis. Write an integral expression for the area of S. So it just says write the expression. We don't have to solve it. So S is 1/2 times the integral from something to something of, it's just r squared. There's no second curve. So I just need to figure out the bounds. But I'm going to write all of this out to begin with. Remember your d theta. You don't want to not get credit just because you forgot. It seems like a small part, but remember d theta represents the width of a tiny little rectangle, and you're adding up a bunch of these rectangles. The expression represents the height of the rectangle. D theta is the tiny width. So it's important. We're going from 0 to pi, but I suspect that this is not pi, right? Because 0 probably gets me here. Let's double check this. We just need to figure out what makes this 0. So when I plug in 0, I get 1 minus 2 times 1, which is -1. So yes, we start back here. Face 0, go backwards 1. And then what would make this 0? So what makes cosine 1/2? Because it's going to have to be 2 times 1/2. So that's pi over 3. 1 minus 2 times 1/2 is 0. Or you could set 1 minus 2 cosine theta equal to 0 and solve. But yeah, that's pi over 3. So those are the bounds here, 0 to pi over 3. It does not say to find the area, so that's it. Just write the integral expression. I think that's because this is no calculator, and they don't want us to do that horrible thing where you square this out. And we could do this without a calculator, but I don't think they're going to have us use that trig identity to be able to do it. Write expressions for dx d theta and dy d theta. All right, so this goes back to knowing that x equals r times cosine theta, and y is equal to r times sine theta. And if I want to find the derivative, I think I'm going to leave them like this and just do product rule right now. So x prime would be first times derivative of the second plus second I should have given myself more room here. Plus second times derivative of the first. That becomes positive 2 sine theta. And we'll clean that up a little bit. Dx d theta is the same as x prime. So this is negative sine theta plus 2 cosine theta sine theta plus 2 cosine theta sine theta. I don't think that you're required to simplify this. You probably could just leave it like that, but I suspect we're going to do something else with this. So that's 4 cosine theta sine theta minus sine theta. So there's dx d theta. Similarly for y prime, it's first times derivative of the second plus second times derivative of the first cleaning it up, you get cosine theta minus 2 cosine squared theta plus 2 sine squared theta. Yes, sines, let's see. Cosine, wait, what is it? Cosine squared minus sine squared is equal to cosine 2 theta. There's no reason to use a trig identity here. I think you can just leave it. Okay, and then part C says write an equation in terms of x and y for the line tangent to the graph of the polar curve where theta equals pi over 2. So, okay, remember we need a point that's in terms of x, y, and we need a slope, which is dy dx. And remember that dy dx is dy d theta over dx d theta, which is why they had us do part B. So let's start with the point. So the point, x of, what is it, pi over 2. And just, you can get a visual here. We're trying to write a tangent line equation for that point right there. Okay, so anyway, x of pi over 2. Remember, your x equation is right here. So it's equal to 1 minus 2 times cosine of pi over 2 is 0 times 0. So 0. I can see that from my graph, right? This point is 0 for x. And it looks like 0, 1. I just want to verify, just in case it's not 0, 1, you know? It also says show work, so I just want to make sure I do that. Y of pi over 2 is equal to 1 minus 2 times 0. Sine of pi over 2 is 1. So 1 times 1 is 1. All right, so the point is 0, 1. And then the slope, dy dx, evaluated at theta equals pi over 2. You're just putting pi over 2 into these equations. So cosine of pi over 2 is 0 minus 2 times 0 squared plus 2 times 1 squared over 4 times 0 times 1 minus 1. So 0, 0, this is 2. That's 0 divided by negative 1. So the slope is negative 2. The equation is y minus 1 equals negative 2 times x minus 0. Or you could write the slope intercept y equals mx plus b. Negative 2x plus 1 is fine as well. All right, I need to... Oh, no, I think we can do one more. Sorry. Okay, is this our last? Yeah. Yeah, this is our last FRQ, so let's go ahead and finish this. This one is parametric. Remember, we did have parametric equations. They were a bit easier, I hope. You just have some formulas to remember. So a particle moving along the curve in the xy plane is at this position for any time greater than 0. Here's dx dt, here's dy dt, and at 4, we're at this point. Remember, I always like to write out, that means that x of 4 equals 1, and y of 4 equals 5. It's easy to, we know we're going to need to use that, and it's easy to assume that's at 0 or something if we're not looking carefully. Find the slope of the line tangent to the path at t equals 4. So dy dx at t equals 4. This is a calculator problem, but you're just plugging in here. So dy dt is like ln of 2 plus 4 squared. What would that be? Ln of 18. Over dx dt, when you plug in 4, is square root of 1 plus 16 square root of 17. So I'm getting about 0.701 for that slope. That's all we have to do for part A. Part B, find the speed of the particle at 4 and find the acceleration. I've noticed in years past that sometimes people find speed and they forget to find acceleration. So that's why I underline things when I'm doing problems. So speed is the square root of x prime of 4 squared plus y prime of 4 squared. And remember, we're not taking any derivatives. We're just calculating this. So that's these two values, right? All right, so square root of ln of 18 squared. Oh, there we go. I want the ln squared, not the 18 squared. Ln of 18, that quantity squared, plus square root of 17 squared will just be 17. So I'm getting 5.035 for the speed. And We don't have any labels on this, so that's it for that. And then find the acceleration. So a of 4 is equal to x double prime of 4, y double prime of 4. Remember, you're allowed a calculator, so you do not have to find these derivative equations. You just have to use your calculator to plug into them. So math 8. So I want to take the derivative of, start with the x, the square root of 1 plus x squared, and I want to evaluate that at 4. And then I also want to take the derivative of ln of 2 plus x squared and evaluate that at 4. And I'm going to round these to 3 places, so 0.970 and 0.444. Doesn't matter if you use triangle brackets or not, but the acceleration should be given like an ordered pair because position was given in that way. Find the y-coordinate of the position at time 6. So this is why they gave us the position at time 4. So remember, this is like a fundamental theorem of calculus problem. I want to find y of 6. So I'm going to start at y of 4, add the change in position from 4 to 6 of dy dt, which is ln of 2 plus t squared. Remember to write dt right there. And that should equal y of 6. And I know that y of 4 is equal to 5. So I'm going to put this in my calculator. So the most common mistake is saying like 0 to 6 or something. That's why it's a good idea to write down what the time is for the position that they gave you. So 11.571 is y of 6. Remember, you have one of these parametric problems on the test and one of the polar problems on the test. So it should be pretty doable. Find the total distance the particle travels from 4 to 6. So remember, this particle is on a curved path. Total distance means arc length. So arc length is the integral from 4 to 6 of the square root of x prime of t squared plus y prime of t squared. And remember again to write your dt. You can fill in the equations for those, but you don't have to. All right, so math 9, 4 to 6, square root. You could put the x prime and the y prime into your y equals if you want, and then just do y1 squared plus y2 squared. I am not going to do that. I'm just going to say, okay, dx dt is a square root equation. So if I square it, it would just come out to be 1 plus x squared. And then I do need to square the other one. So the other one is natural log of 2 plus x squared. Close the natural log, close parentheses around it, and square that. And I'm getting 12.136. This popped up really fast on my computer calculator, but I remember when I did this on my handheld calculator, it had to think for quite a while before it gave me this answer. So don't be alarmed if that happens to you. I don't know what takes it so long, but it will get there. So just wait for it. All right, I think that was it for the free response questions. My last video will tackle the multiple choice problems.